Hey folks, a very good evening and thank you for joining in this evening. So could you please confirm in the chat window if you're able to see my screen and if you can just see and if you can hear my voice, because then we can get started. It's already 7, so we'll right away jump into the discussion itself. So can you please confirm in the chat window if everything is all right? I hope my chat window is working as expected. Yeah, so okay, cool. So everything is good. Good. Okay, good. Yeah, you'll also have less noise because I'm back in Hyderabad to my home studio where you have much better audio. I had to travel because I had a family emergency. So I was almost out of station for 6 weeks. I just came back and things are looking good. Yeah, the audio quality also hopefully improves as compared to the last few weeks of sessions, which I was doing from Vishakhapatnam. Anyway, cool. So let's get started with today's session. So today is the third live session for DBMS for problem solving. And we will be covering transaction and concurrency control, file structures with a specific focus on B and B plus trees. Again, in GATE, you can typically expect about 3 to 4 marks from just these topics. And to be very honest with you, these are extremely easy concepts. The questions that you encounter are very easy and you can easily score these 3 to 4 marks. But what is the catch? There is also a catch here. The number of concepts, right? So the number of concepts that you have, right? And the number of concepts that you have in transaction and concurrency control, B plus trees is not a very complex concept because if you know the basic data structures, it's very straightforward. But as far as transaction and concurrency control is concerned, there are a lot of concepts. Okay, somebody says the full screen is not clear. Is it so? I thought we are on full screen. So let me just check on the video. Is there a problem with the full screen, folks? Is there any problem with the full screen? Are you able to see whatever is there on the screen? Is that visible? Just let me know, because I've set it to be fairly clear. Yeah, everything is clear, right? Yeah. So anyway, so let's go back to the topic and okay. So the catch here is the number of concepts is quite large while the problem difficulty is low, which means the problems are easy to solve, but it's very easy to get confused given that there are a good chunk of concepts and they're very easy to get confused, right? Like especially with respect to conflict serializability, view serializability, all of those concepts can become confusing if you don't revise. But if you know these concepts, if you know the definitions, if you know the basics, this is extremely scoring, right? So that's why you might find many questions in this session to be on the easier side if you know the concepts, right? So this is the first question. Let's get started. Again, this is a typical medium difficulty problem as far as GATE questions are concerned. Again, we have started putting this hardness here primarily so that you know whether it's again, we are mostly focusing on easy and medium questions because this is the first iteration of this subject. We will do hard questions in the future iterations. Okay, while you answer, I'll also put in some answers. I hope our team also will join soon. I'm sure. Oh yeah, so some of our folks have also joined in. Yeah, cool. Folks, please focus on solving the problem. We can discuss other stuff later. Anyway, good evening to all those who are wishing that. But let's solve this question, right? Because this will be helpful for you. Again, if you just know the concept of conflict equivalent serialize or conflict serializability, it should be fairly straightforward. Most of transaction control is common sense. Of course, you have to know the terminology a little, but otherwise the logic is very straightforward. Okay, people have started putting in the answers. Somebody is asking about revision. We have a session tomorrow. Please try to attend that. I'll also focus on how to avoid forgetting concepts and how to revise faster in tomorrow's session, right? Again, I'll let some of our teammates and mentors answer some of the questions, general questions in the chat window. Okay, somebody says 2, somebody says 7. Okay. Okay, somebody says 1 is the answer. Okay, let's okay, somebody says 3 is the answer. Okay, the answers are all around the place. Somebody says 7. Okay. Okay, again somebody says 7. Okay, the answers are all around the place, but that's okay. Okay, somebody says C3. Okay, try to solve the problem. I'll give you maybe a minute more and then I'll explain the solution also. I think we have about 9 or 10 problems today. Again, please try to solve the problem. Think of how do you come up with conflict serializable schedules, right? So if you can think about it from that perspective, again, those of you who might need a hint, okay, let me write a hint for you. So use dependency graphs here, right? And then topological sort, right? So these are the two concepts that you need to use to come up with the answer for this. Okay, I hope some of you who are not able to figure out how to solve can, I hope you understood when the moment I said dependency graph. Again, just draw a dependency graph across all these transactions with these transactions as nodes. It's a very standard process, right, in transaction control. Okay, I've seen, I mean, the answers are all over the place. If you see the answers here, they're all over the place. 7, 3, 1, 2, 4, everything. So anyway, so let's dive into the solution okay, I'll wait for a few more seconds, then I'll jump into the solution itself. Again, this is not a hard problem. This is a medium problem by gate standards. Okay, so let's tackle this problem, right? So you have T1, T2, T3, T4. Let's draw the dependency graph. T1, T2, you have T3 and T4. I'm just drawing it because, so if you notice, what do you have here? You have read followed by write. Read A, write A, right? So this is reading, then T1 is writing, right? So this generates this edge. Okay. Again, I hope you understand how to draw the dependency graph. I will not be able to explain it in a problem solving session. I'm assuming that you know that, right? So because of this read followed by write, again, this is your timestamps, right? So this is your timestamps, right? So because of this read followed by write, you get this edge. Then let's look at T2 also has an edge to T3. Look at this, because there is this WC, right? T2 is writing, then T3 is writing. Okay, because of this, you get this edge, right? Next, look at this. T2 also has an edge to T4. Okay, the reason being you have a write here and then you have a read of the same variable, right? You have write on C, you have read on C. That's why you have this edge. Now T3, T4, is there any edge possible between T3, T4? Yes, because of this. Look at this, you have a write followed by read, right? So because of this write read, you have this edge also, right? I think I've covered all the cases here, right? Yeah, so this will be the dependency graph. Again, I've solved this problem before coming to the session. This is how the dependency graph looks like. Okay, so the moment you arrive at the dependency graph, the problem is more or less straightforward. Now, using this dependency graph, try to create serial orderings. Now, to create serial orderings, the easiest way is to start performing topological sort. Now, the easiest way of thinking about it is take a node with in degree equals to 0. So amongst all these, say this is a directed graph that we have, right? Look at a node with in degree equals to 0. This does not have in degree 0, in degree not equals to 0, in degree, this has in degree equals to 0, right? So your first transaction that will be completed is T2. Now T2 can be followed by, let's start writing that part, right? So T2 can be followed. So if first you complete, because we want serial orderings, right? Suppose if you just complete T2 first, then you can get rid of this edge, you can get rid of this edge, you can get rid of this edge, right? After that, the only other dependency that you have is T3 before T4. That's the only thing that you should ensure. So I can write it as T3, T4 followed by T1. This is one valid thing. Remember that T3 should be before T4. That's the only rule, except that all possible orderings. So we'll start with T2, T3, T4, T1. Here notice that T3 is there before T1 in the serial order, right? Similarly, I can also order it like this, T1, T3, T4. Even here, because there is no edge from T1 to T3 or T4. There is no such edge. So T3 in the serial order, I can place it anywhere. I just have to ensure that T3 is before T4. Again, T2 is the first one, obviously, right? So T2 is obviously the first one. Next comes, you have T3, T1, T4. This is also a valid ordering. Right? This is also a valid serial ordering, right? The reason this is a valid serial ordering is because you have T3 before T4. That is the only constraint that you have to satisfy. T1 can be there anywhere. Now, if you notice, you get three orderings, T2, T3, T4, T1. This is one serial ordering, which is conflict equivalent to this. You have T2, T1, T3, T4, T2, T3, T1, T4. You have three possibilities, right? So for any problem like this, the easiest way to solve is first to draw the dependency graph and then try and come up with these orderings. These orderings, again, you don't have to use the concept of topological sort. You can start with a node which has in degree equals to 0. Start with that and try to come up with orderings which preserve these dependencies, or in other words, these orderings, right? So I think again, this is a very straightforward problem. We have explained tons of problems like this in our course videos also. If you do not know the concept, of course, this will feel like Greek and Latin. But if you know how to construct a dependency graph given a set of transactions, this is a straightforward problem, right? So again, if you don't know the concept, don't expect to understand it, because the fundamental assumption that we are making in this session is that you've prepared for these concepts, and this is a practice session. If it's all about learning, this practice session is not meant for learning. Because if I have to explain the whole concept of how to construct dependency graphs and why topological sort is the right approach, we spend almost 1 hour in our course videos explaining these concepts, right? So I don't think we can cover it in depth in a problem solving session, right? So sounds good. But this is, again, given a problem like this is how you can tackle it and solve it easily. Again, we have solved tons of problems in our course videos. Again, you can find similar problems in most textbooks, in most previous year questions also, if you want to practice, if you're not a course registered student. Okay, cool. So now let's go to the second question. Okay, this is a good question. Again, this is a B plus tree. Again, if you're a course registered student and if you have any questions about the explanation, shoot an email. We'll try to respond back to you as soon as possible. But please watch the corresponding concept videos and solve problems. Otherwise, you'll not be able to understand this. That's very important. Again, this problem, you can easily make silly mistakes. So please be careful with this. It's very easy to make a silly mistake here. So please be very careful. Please try to draw the diagram of a non-leaf node in B plus trees. Okay, some of you have started putting in the answers. I see 92, 63, 64, 93, 49. Okay, again a wide spectrum of answers. Okay, I think some of you got it right without doubt. Again, if you know the concept of B plus tree, if you can visualize a non-leaf node in a B plus tree, this is very straightforward, right? So again, as a hint for some of you who are still solving, if you think of this as a non-leaf node, right? If you think of it as a non-leaf node in a B plus tree, how does it look like? You have pointer 1, then you have key 1, you have pointer 2, key 2, so on and so forth. Key n minus 1, pointer n, right? And the order is nothing but n, right? The order of a non-leaf node is nothing but n here, if this is the structure that you're drawing, right? So use this diagram always, whenever. It's very important skill to start drawing diagrams. Okay, now it's straightforward. With this diagram, I think this is just simple arithmetic now. Okay, many of you have put in your answer. So let's dive into the solution. So it says, so if you read the question, right, it says the search key is 6 bytes. So this is 6 bytes. So this is 6 bytes. So on and so forth. This is also 6 bytes. What about the pointer? The pointer is, okay, the pointer is, 1 second, the pointer is 5 bytes or 10 bytes? Okay, a record pointer is 10 bytes. And a block pointer is 5 bytes. Yes, right? So we are looking at block pointers, right? So this is 5 bytes, right? You should not be using the 10 bytes because we are talking about the order of a non-leaf node, right? So, okay, so a block pointer is 5 bytes. So you have 5 bytes and 6 bytes. So if you start writing an equation, 5 times n, right? Because you have n pointers, plus 6 times n minus 1, right? Because you have n minus 1 keys. And what is the size of the block itself? The block itself is 1024 bytes, right? So this should be less than equal to 1024, right? Obviously, makes sense because this whole thing is stored in one block in a B plus tree. Now, if you simplify this, you get 11n is less than equal to, you take 6 that side, you get 1030. So you get n is less than equal to 1030 by 11. Now what is 1030 by 11? You get 93.63, right? And remember that n is an integer, right? So what is the maximum value of n which is less than equal to 93.63? It is 93, not 92, 93, right? Many of you got it right, right? So it's a very simple thing. You just have to visualize how a non-leaf node in a B plus tree looks like. This 10 bytes is given just to confuse you. If you have this visualization, this math is extremely simple and straightforward, right? Very simple problem if you think about it. So 93 is the correct answer here. So let's go to the next problem. Again, here we're talking about a B tree, not a B plus tree. As somebody says, the whole objective of these questions is for you to revise concepts that you have already learned. And our objective here is to do multiple iterations of each subject so that, of course, we'll do faster iterations as we come closer to the examination. The whole objective is to help you in revision and practicing. Again, this is a B tree of order 4. For those of you who may get confused, if order equals to 4, that implies that the maximum number of keys is equal to 3. Okay, in case you have forgotten that basic concept. Just wanted to give you that hint so that you don't do silly mistakes. Okay, I start seeing people putting in answers. Again, please think carefully of how the B tree will balance itself. Guys, a very common mistake that I see here is it's a B tree of order 4, which means any node can have maximum of 3 keys. It can't have 4 keys. Some of you have given answers with 4 keys. That's not even possible, right? So it clearly saying that it consider a B tree of order 4, which means number of keys will be 3, or maximum number of keys will be 3. I'm sorry. Okay. Aha, I understand how. Okay, so I think we should have. Okay, I got the confusion. Okay, got it. Okay, we should have been more careful with the framing of the question. Okay, cool. So I think we could have framed the question better. Okay, so list out the left children. We could have said left children of 28, or right children of, sorry, not left, right children of 28, right? So we could have said the right children of 28. I got the point. Now I understand why people are saying 25, 30, 40, 42. I got it. I think we should have framed it better. Okay, we will take a note of it. Okay, cool. So let's look at it. First, we want to insert 42. So 42 always has to go here. But here you can't have 4 keys. You can only have at most 3 keys. So what will happen here? This 28 will get pushed up now. Right? So the 28 will get pushed up. And then you'll have 25 here. So how will it work? You'll have 25 and this won't be here. 30 and 42. So this part will point to 25. This will point to 30 and 42. Right? So 28 goes to the parent. Next you're inserting 40. So 40 is also greater than 28. So 40 will be inserted here because it can accommodate 3 keys. No more splitting needed. Right? So when we said the children of 28, we meant the children corresponding to the pointer after 28. That's what we meant. So if that's the question, the answer is this. These are the right children. The left children will be 25. So yes, I agree with you that we could have formulated this question better, but I got where you're coming from, right? So cool, sounds good. So yeah, so 25 will be the left child of this node 28. 30, 40, 42 will be the right child. Yes, I completely agree with you that we could have written the question more carefully to avoid confusion. But yeah, thanks for that point. Yes, cool. So again, this is a very simple, easy question. This is just about, do you know how to insert values and how to rebalance a B tree? That's why we just noted that this is an easy question, right? Cool. So let's go to the next question. Again, this is also a fairly easy question. Most questions around these topics are easy in Gate, but these are easy amongst the easy. Again, please read the question carefully. This is I would call it a trivial question actually. Not even an easy question. I would call it a trivial question. If you read the question, you should get the answer in a second. Yeah, some of you are saying 4, 2, 5. The answer is 1, guys. This is like common sense, right? If you know, look at this. We are talking about what is the minimum number of keys in the root node. Imagine there is only one element in your whole B plus tree. Where it will be stored? It will be just stored. Again, the number of keys in an internal node can be 5. You can have up to 5 keys, right? You can have up to 5 keys. But the minimum number is always 1. All right. Imagine, I mean, as an extreme example, imagine you have a B tree in which you have only inserted one element. So your root node will contain that one element. So the answer here is 1. Right. So if you just read the question carefully, it's trivial to understand it. Again, cool. So let's go to the next question. Yeah, because there are so many concepts here like locking, two-phase locking, conflict serializability. It can get, again, we are tagging this question as easy because if you know the basic properties of conflict serializability and two-phase locking, this is straightforward. And of course, multi-granularity locks. If you just know these concepts at a very high level and some very basic properties, these are straightforward. Again, please read the options very carefully. I see some of you putting in the answers, your option is incorrect or your answer is incorrect. Just read the options carefully, please. Okay, a lot of you are putting in D. Okay, so let's go into the solution. In case if the solution that I'm giving is incorrect, just let me know. Okay. So let me explain. Okay, I think this part is very easy. Anybody who has studied about two-phase locking, this is straightforward, right? Remember that if you have two-phase locking, right? Two-phase locking implies conflict serializability, right? If you use two-phase locking, you're guaranteed to have conflict serializability, but not the other way around. The other way around is not always necessary. It's not necessary that every conflict serializable schedule have to be generated by a two-phase locking. Okay, so it's a one-way direction. Two-phase locking, if you use two-phase locking, you're guaranteed to get a conflict serializable schedule. But every conflict serializable schedule need not be generated by a two-phase locking. So this statement is surely incorrect. Now, when you're using a multi-granularity locks, right, typically what happens? Your locks are acquired. So how does that lock acquisition happens? Lock acquisition happens top down, right? And how does that lock release happens? Lock release happens bottom up, right? So lock acquisition happens top down, right? Lock release happens bottom up, not top down. That's why I told you, please read the statement carefully. It says in multi-granularity locking, which means you can lock at different granularities, as the name suggests. Lock should be acquired and released from top level to bottom level. No, should be acquired top to bottom, right, top down, but released bottom up, right? So this statement is also incorrect because both of them are incorrect. Option C is the right option, right? I think some of you got confused with the none of the above. I think some of you thought none of the above basically means both these options are incorrect. But the actual true answer here is both S1 and S2 are false, right? So that's the right answer here. Again, I completely can understand that some of you getting confused. Again, I think some of you got confused with D because you thought, okay, this is incorrect, so none of the above is the right answer. So that's why you should read the statements given carefully, and you should also try and read the options very carefully. Number 2. Again, another possible error that students could commit in this is, again, not reading this statement itself correctly, right? So that's another problem, right? For S1, I think most of you would get it right because you know that two-phase locking basically implies conflict serializability, but not the other way around, right? So that's why we mark this question as easy, because if you know the definitions, this is straightforward. Typically, questions like this can be asked for 1 mark in GATE. Again, this is tricky, but not even, again, this is tricky, but if you know the definitions, it's a straightforward problem. Okay, so let's go to the 6th question now. Okay, I hope it is clear and visible. Okay, anyway, I hope this is, you got it right. This is right A. I hope that part is clear. Again, please read all the options very carefully. This is all about conflict serializability and view serializability. Okay, I see people putting in the answers. Again, please be careful when you read it. If you know how to determine view and conflict serializability, this is a straightforward question. Okay, some of you got it right. So let's go into the solution itself. So the first statement here says that the schedule is conflict serializable, right? So if you start drawing, so you have T1, T2 and T3, right? You have 3 transactions here. Now, very simple rule that you have to observe, simple thing that you can observe here is look at T1 and T3, right? So this is your T1, this is your T3. So if you notice, you have write A followed by read A. Look at this, you have write A and read A, right? So because of this, you will have T1 to T3, because whatever T1 has written, T3 will read it. That's one. Now look at another thing here, which is, okay, look at this. You have write B, then you have read B. So whatever T3 is writing, T1 is reading. So if you start drawing the dependency graph, you'll see, again, there are other parts to the dependency graph. I'm not drawing the full dependency graph. But if you just look at T1, T3, you observe a cycle here. Because there is an edge from T1 to T3 because of write A, read A. There is an edge from T3 to T1, right? Because of write B, read B, right? So because of these two, you're getting a cycle here. The moment you have a cycle in this graph, again, I've not drawn edges between T1, T3, T3, T2. I don't have to draw everything. By just observing this simple pattern, the moment you have a cycle basically implies that it is not conflict serializable. That's one of the simplest ways to determine conflict serializability, right? So S1 surely is incorrect, right? Okay, next, what about S2? Now you can also follow how to check view serializability, right? So there is a very standard way that we explain in our course videos that you can also find in most textbooks, which says, how can you come up with view? So the way you determine that this is view serializable is you make it view equivalent to a serial schedule. You can go down that route. That's one way of solving it. But I wanted to introduce you to a very interesting but a simple concept. There is a very interesting property between view and conflict serializabilities. The property is this. Again, you don't have to apply this property to solve this problem, but the schedule, again, there is a very interesting property that I wanted to introduce you to if you don't know it. Okay. So any view serializable schedule that is not conflict serializable must contain a blind write. Okay, this is a very interesting property of view serializability and conflict serializability, right? So notice that any view serializable schedule that is not conflict serializable must contain a blind write, right? Now you can determine if this is view serializable because we know that this is not conflict serializable. So for this to be view serializable, it must contain a blind write. Okay, are there any what is a blind write? Blind write means you're writing without reading, right? Look at this. Before this write, there is a read. Before this write, there is a read. Okay, before this write, there is a read. Before this write, there is a read. Before this write, there is a read, right? So there are no blind writes here in this schedule, right? In whatever is given to us, there are no blind writes, right? If this were to be view serializable, because we already know that it's not conflict serializable, for it to be view serializable, it must contain a blind write. The fact that it doesn't contain blind writes means that it is not view serializable also. So this is a very interesting property that you can use. Again, if you don't know this property or if you don't want to use this property, you can always do the standard way of checking view serializability by doing view equivalent to serial schedules, right? That's another approach. Again, if you recall, you have initial write, final write, update, read, that strategy, right? You can also apply that strategy to determine that this is not view serializable. But another way of doing it is this. This is something that I think many students may not know. So we thought we'll introduce this here. It's a very interesting property to think of, connecting view and conflict serializability. Cool. So now given that both are incorrect, which of the options are correct? None of the above, right? So sounds good. Again, blind write basically means what? Blind write has to be on the same data, right? So both of them are false. So none of the above is the right answer, because which of the following options is correct? That's the question. So D is the right option here. So blind write always should be on the same variable, right? Because you're reading before writing. Then it's not a blind write. Blind write means you're not reading anything. You're just brute force, blindly you're writing things without reading them before. That's what is a blind write. On the same variable, obviously, right? So cool. Sounds good. So this is a very interesting question. Okay, cool. Let's go to the next question now. Again, this is a straightforward question. This is actually fairly easy. Again, somebody is saying, why make the solution harder? The objective here is not to make the solution harder. I wanted to introduce you to a new concept and a new property. That was the whole objective. I hope you appreciate that. I wanted to give you a different way of solving the previous problem. The standard way is also there. You can also solve it using that. Okay, I think most of you got it right. It's a very simple question. If you recall this whole diagram, so this is basically number of transactions or number of active transactions to be precise. This is your throughput, right? So what happens is beyond a certain value, beyond a certain value of number of transactions, you have the trashing problem, right? So standard diagram that you see in most books. But if you have read-only transactions, there is, read-only is you're just reading from the data, right? So you don't have to worry about any locks. You don't have to worry about anything, right? So lock trashing itself will not occur because you don't have to lock anything. When you have read-only transactions, you don't have to read anything, right? So read-only transactions do not need, okay, sorry, my bad. So let me write it this way. So with the increase in transactions, lock trashing can be observed. Certainly in read-only transactions, you don't observe lock trashing because you don't have to lock it in the first place, right? If you have read-write transactions, obviously locks need to be there. This whole diagram is valid when there are both read and write operations. So this option is certainly true, but let's read the other options. In both read-only and read-write transactions, no. In read-only, you don't have lock trashing. Only in read-write you have lock trashing. So this also can't be the answer. None of the above obviously is not an answer because B is the option, right? Again, here the whole question has been written just to confuse you a little. Again, you know that for read-only operations or for read-only transactions, you don't require locking. You can just read. Only when you have read-write that you have to start locking. And when you have locking, obviously, you will encounter a lock trashing issue, right? Cool. Okay, let's go to this. Oh, this is a good question. I remember doing a video on lock trashing. I remember drawing the diagram and explaining it for sure. In case it's missing, we'll re-add it to the course videos. Okay, so Okay, people are putting in their answers. I think it's hard for me to type in the chat window while looking at answers. Okay. Okay, most of you got it right. Again, it's not a hard problem. If you know the concept, it's straightforward. Okay, so let me explain the solution here. Again, it's fairly straightforward. First, let's look at S avoids cascading rollback. Right, look at this. If you notice, look at these two. Right, so transaction 1 is writing on X. Then transaction 3 is reading on X. Right, and if you look at the commits here. Now imagine in this order, T1 aborts. Right, so let's assume T1 before committing aborts. So both these operations are run, and let's assume T1 aborts here. Then what do you have to do? Remember that transaction 3 is reading the value that transaction 1 has written. So if T1 aborts at this time without committing, then you have to roll back T3 also, right? Because T3's read is after T1's write on X, right? So if T1 aborts at this time, right, this implies that T3 has to be rolled back, right? Common sense, because your T3 is reading X which T1 has written. For some reason, if T1 has to be aborted here, we have to roll this back. So S does not avoid cascading rollback, number one. Now S is recoverable, right? Yes, S is certainly recoverable if you think about it. Okay, so again, recoverable, certainly that's a valid point. Remember that your T3 is reading the data after T1 and T2 are writing the data, right? Look at this. Your T3, your transaction 3 is reading the data after transaction 2 and transaction 1 are writing the data, right? So, and T3 commits after 1 and 2 have committed, right? In case there is any problem, you can always roll back, right? In case there is any problem here, in case, suppose, let's assume at this point T1 dies, right? Or T1 is aborted, then you can always roll back, which means S is recoverable, right? Remember that again, for any sequence of events here, wherever either T1 or T2 or T3, wherever T1, T2, T3 abort, we can always, at any point if they abort, right? Remember that T3 is committing after T1 and T2, right? So we can roll back. We can roll back the operations, and the moment you know that you can always roll back, that implies that this is recoverable. So obviously this is the right option, but let's keep in mind and check the other two also, right? So that's important. Okay, it's always good to check all the four options if time permits, right? So okay, let's look at this. If you, for this it says conflict serializable, right? So let's draw the diagram. T1, T2 and T3. So if you draw the dependency graph for this, it will look like this. Again, you can cross check it. I've drawn it earlier, right? It look like this, right? So in this dependency graph, you have a loop or you have a cycle, right? Since you have a cycle, obviously it's not conflict serializable, right? Obviously. So what about strict serializability? Remember, T3 reads, T3 is reading the data before T1 and T2 are committing, which means obviously this is not strict serializable, right? So obviously B is the right answer, which most of you got it, right? So straightforward question there. Cool. So it's recoverable. It doesn't avoid cascading rollback. It is not conflict serializable. It is not strict. Okay. Cool. Let's go to the ninth question. Again, there will be some overlaps with respect to locking concepts in databases and operating systems. Because at the end of the day, the databases use the locking mechanisms that operating systems provide, right? So there is some concept overlap there. For example, trashing is something that you see in operating systems also. Yeah, most of you are getting it right. This is literally a textbook example problem, right? If you know how to do the timestamp based ordering protocol and Thomas Wright rule, it's straightforward. Okay, I think most of you got it right except for one or two of you. This is an easy problem. The reason it's easy is if you just know the definition of how TOP and TWR work, you can easily understand how everything works. Okay, so let me explain this concept here. It's fairly straightforward. Again, just remember that you have to have timestamps for each transaction and read timestamps and write timestamps for each of the variables. That's the whole concept, right? So you have R1x, which means the read timestamp of x equals to 1, right? And the timestamp of transaction 1 equals to 1, right? Then you have W2x, right? So then you have timestamp of T2 equals to 2 and the write timestamp of x equals to 2. Then you have W2y, right? So write timestamp of y equals to 2, right? Then you have, okay, so then you have W3y, right? So let's write W3y. So now you have timestamp of T3 equals to 3. And notice that timestamp of T3 here is greater than the write timestamp of y, which is equals to 2, right? So remember the write timestamp here, I hope this is clear, right? So the timestamp of T3 is greater than, okay, the timestamp of T3 is greater than write timestamp of this. This is cool. Now let's go to the next one. Next one is this W1y, right? So when you have W1y, what happens here? Then you only have commits after that, right? So let's see what happens when we have W1 or first transaction writing on y. Now what do you have? You have, if you notice, the write timestamp of y equals to 2, right? The write timestamp equals to 2. 2 is greater than, what is the timestamp of transaction 1 here? The timestamp of transaction 1 equals to 1, right? So this creates the problem, right? So the schedule will not be permitted if you're using a timestamp based protocol. Remember the simple rules of timestamp based protocol. If you're using timestamp based protocol, in timestamp based protocol, this will not be accepted. The write timestamp of variable that you're writing now, which is 2, is greater than, right, the timestamp of the transaction that you have. So this will create the problem. So certainly this is not timestamp based protocol. Obviously this will not be this also, because this says both TOP and TWR. But the second option, let's look at the second option now. Timestamp based ordering with Thomas Wright rule, right? So the moment you apply Thomas Wright rule, what happens now? Let's see what happens now, because all of this stays the same. The only part that will change here will come with respect to this, right? So with respect to this, let's see what happens. You have everything else stays the same, right? With respect to this, let's write down what exactly happens here. Here you have timestamp of t1 equals to 1, which is less than the right timestamp of y. What is the right timestamp of y? Right timestamp of y equals to 2, right? So in this condition, what does Thomas Wright rule say? Thomas Wright rule says if this is the condition, we simply ignore this, right? That's what Thomas Wright rule basically says, right? Whenever you encounter this, you simply ignore it, right? So in timestamp based, see what are we doing here? We are doing timestamp based ordering itself, but when you apply Thomas Wright rule, this will not break the whole system. Thomas Wright rule basically simply says that ignore this, right? So this schedule will be permitted if you're using a timestamp based ordering with TWR, right? So B is the right answer, as most of you got it, right? So cool. Sounds good. So let's go to the 10th question now. This is a very good question. This is the best question of the day actually. I loved solving this. I think this is a assignment problem or a final exam problem at IITB. Again, all of these questions will be added in the course videos at the respective chapters or modules, so that in case you have not completed these concepts, you can always come back to them, or you can even watch these videos as part of your revision. So don't worry about it. For all the course registered students, you will be able to access all of these live sessions as part of the course videos in the appropriate order. This is the best question of the day. This is actually a very real world question. Again, somebody thinks that these are hard questions. These are not hard questions. You just have to sit and practice more. Karan, especially you, I think you have to sit and practice questions. There is no shortcut here. Some of them are medium, they're not even hard. If you're getting demotivated, it's most likely because you're not practicing enough. And you have to revise and practice. There is no shortcut there, guys. If there was a shortcut, I would tell you that. Again, Karan, you just mentioned that some of the live sessions haven't been added to the course videos. Most of them have been added. Some of them which are not added, we'll add them by tomorrow. Okay. Again, you can't skip practice. These are all gate level questions, guys. I have not given some extraordinarily hard questions. I mean, this question itself has been taken from an actual assignment or a final exam at IITB, because you can expect a question like this for 2 marks in gate. And this is not hard. If you know the concept of B plus trees, this is like cakewalk. Again, please read these questions carefully. It's a lengthy question to read, but it's an easy question if you know the concept of B plus trees. Again, any of your registered students who are getting little demotivated, please reach out to us. We'll certainly help you. But you can't skip practice. Don't expect to get a good gate rank without putting in the effort. That's not going to happen unless you're a genius. Again, read the question carefully. It looks lengthy, but it is simple and straightforward. I see a few of you putting in the answers. Just be careful. You're almost there. Just be a little careful, you'll get it. Again, I think some of you are counting the actual data that is stored in the disk also. Please avoid counting that in the levels. You should only count the tree levels, not the actual data that is stored in the disk blocks. This is a very real world question. I love the fact that this is an actual system that you'll encounter in the real world. Okay, so let's go into this question, right? So it's a good question. So let's write down the details here, right? So okay, first and foremost, it says each block is, where is the block size? Yes, each block is 2048 bytes, right? And it also says that each tuple in this table takes 50 bytes. Each tuple takes 50 bytes. So let's ask ourselves this very basic question, right? So let's ask ourselves this very basic question, which is how many tuples per block? Okay, how many tuples can you store per block? Okay, the tuples you can store per block is 2048 by 50, right? So which is equal to 40, right? Of course, you have to take the floor of it, right? Because you can only store an integer number of tuples, first and foremost, right? Now it also says, if you look at the question, it says there are a total of 8 million records. Total of 8 million records. Now to store 8 million records, number of blocks needed. Number of blocks needed to store 8 million tuples or 8 million records. 8 million is 8 into 10 power 6, right? And per block, you can store 40 tuples. So if you divide this by 40 and take the floor of it, what will you get? So this is 2 into 10 power 5. These are the number of blocks that you need to store 8 million tuples or 8 million records, right? This is important because now what you know here is this: the final data that you have on the disk, the whole thing that you have on the disk itself, this is 2 into 10 power 5 blocks in which the actual data is stored, right? This is the actual disk blocks on which, because using this simple data, you realize that you need these many blocks to store the raw actual tuples or records, right? That's important. Next. Okay. What else do we know? We know that, what else are we given? Okay, 20 years. Okay, these many records, 10,000 students, all of that is cool. The order is 9, the order, right? The B plus tree with order n equals to 501. So what does this imply? This implies that in the worst case, let's talk about the worst case. In the worst case, you will encounter 50 pointers. You will encounter 50 pointers in the leaf node, right? And you will have 51 pointers in the internal nodes, in the worst case. Not the root, the other internal nodes, right? So if you notice this, again, because n, which is the maximum number of pointers in a node, again, remember that it's a B plus tree. So the leaf nodes will also have this side pointers, right? So that's why I wrote 50 pointers in the leaf node, 51 pointers in the internal nodes, right? So if you think about it diagrammatically now, look at this. You have this, okay, these are your leaf nodes, right? So these are the leaf nodes of your whole B plus tree. This is your actual disk, right? So this can have 50 pointers here. There could be 50 pointers here, 50 pointers here. This one pointer is to the next, because it's a B plus tree. All the leaf nodes are connected like this, right? So you could have 50 pointers, so on and so forth, right? Now look at this. You have a total of 2 into 10 power 5 blocks. Okay, so let me erase this and write the math here. I'll write the fact that this is a disk here. Okay, so you have 2 into 10 power 5 blocks and you have 50 pointers, each pointer pointing to one block. So how many such nodes will be there? That you can compute by saying 2 into 10 power 5 by 50, right? So 2 into 10 power 5 by 50 will be 200 by 50 is 4, and you get 4,000, right? So you can have 4,000 leaf nodes here, right? You can have 4,000 leaf nodes here, because each leaf node is, in the worst case, the leaf node will have 50 pointers. So 50, 50, 50, 50. So you're left with, so you have 4,000 nodes here. So if you have 4,000 nodes here, now let's look at the internal nodes here, right? Each internal node can have 51 pointers below, right? This can have 51 pointers, this can have 51 pointers, this can have 51. You don't need these edges now. You don't need these pointers now, right? So how many such nodes, how many such internal nodes at this level will be there? At this level, right? It is nothing but it is nothing but 4,000 by 51. 4,000 by 51, of course, the seal of it, which is equal to 78. So you can have 78 internal nodes here, right? And you have a root node. The root node can have all the 78 pointers, because the maximum it can have is 101. So we'll have all the 71 pointers. Now what is the question here? The question says the number of levels in the B plus tree. Root, 1 level, internal, 1 level, leaf, the 3rd level. Don't count this, because this is actually data stored on the disk. These are your leaf level nodes. Your B plus tree is only this structure. This structure has 3 levels, right? So the answer here is simply 3, right? I hope this is clear, right? Yes, the order is 101. I understand that, but we have to think of the worst case, because the question says the number of levels that the B plus tree uses in the worst case. That's why I wrote this. In the worst case, half of your nodes or half of your pointers will be full. That's very, very important. The worst case is a very important part here, right? That's something that many people miss, right? B trees, B plus trees ensure that at least, except for the root node, everywhere else it wants to have at least half the pointers full, right? So that's the whole concept here. Again, very importantly, I see that some of you are getting little demotivated, but please understand that you don't prepare for GATE in just a few days. it requires practice and consistency, right? So if you are a course registered student, I can talk to you much more easily, because for a course registered student, I can simply tell you that you have a lot of easy examples that we solve in the course videos, right? We have thousands of problems that we solve as solved problems in the course videos along with previous year questions. So the best way to learn is learn the concept, solve the easy problems, then you have practice problems, right? Then you have test series problems, right? So you have almost close to 5,000 plus problems just in practice and test series problems in our course videos, right? So it requires practice and consistency. There are no shortcuts here, folks. If somebody tells you that there is a shortcut, I think he's just making a fool of you. Okay, if there were shortcuts, I'm sure I would have learned about it, because we have seen at least 10 years worth of toppers. Personally, I have seen at least 10-12 years worth of toppers in GATE, right? I don't know a shortcut. So it is practice and persistence and consistent effort. Some of you may be concerned that I'm not able to solve some of these problems. That's okay. You don't become a brilliant problem solver overnight. You learn the concept, go through the easy problems, go through the solved problems in the course videos. Then you will understand how to do it. And of course, you have to keep revising. That's why tomorrow we created a session on how to make short notes so that you can revise a subject faster. Our objective in this whole session would be, how can you revise a whole subject in 4 to 6 hours, or even less if possible, right? So this revision strategy, again, we have given detailed notes or long form notes that are available for everyone, including our course students, right? So tomorrow we'll discuss about short notes, and from next week we will start the operating system subject, right? So we are done with DBMS. We will start the first iteration of operating systems from next week. And tomorrow we have a session on how to prepare short notes effectively so that you can learn concepts in 4 to 6 hours. Okay, cool. Sounds good. And anybody who thinks one of our answers is incorrect, please do reach out to us. If there is an error, we will always cover it. And all the live sessions will not be on YouTube. Okay, let's make that very clear. I think I've mentioned this earlier also. We want to do some of these live sessions, especially students who are preparing for GATE. We will do some of these live sessions publicly on YouTube, but moving forward in the near future, we'll surely make them only for our course registered students. We have to do that. Okay, number one. Number two is anybody who is a course registered student who is struggling with anything, do shoot us an email. We will certainly revert back to you faster. If you are not a course registered student also, it's okay to email us, but we cannot guarantee the speed of answering. We will answer if time permits, or else we will not be able to answer your questions. Okay. Thank you very much. Again, this is my best question. This is the most real world question amongst all of the sessions. And I love this question, to be honest with you. Okay, folks, thank you very much. See you tomorrow again at 7 p.m. Bye-bye. Please